All right, so chapter 7, chemical reactions, we're finally getting into, well, I shouldn't say we're finally getting into. We've been talking about chemical formulas and stuff, and that's super important because if you don't know what chemical formulas are, then chemical reactions aren't going to make very much sense because they're essentially the words and the chemical reaction is the sentence, right? So this is building up a whole really language of chemistry. You might have done this experiment in grade school or even more recently because it's fun. You can take, chemical reactions involve transformation of one or more substances into different substances. One example of that is taking sodium bicarbonate or baking soda and reacting it with vinegar to form CO2 gas, water, and sodium acetate. And so the carbon dioxide bubbles out of the mixture, and you add a little bit of soap to it, so it forms a whole bunch of bubbles, a little red food coloring, so it looks like lava. You got yourself a volcano. Reactions that occur in liquids and form gas are gas evolution reactions. We'll talk more about those, but that's just one type of reaction. You can actually do this experiment or a similar experiment with hydrogen peroxide and potassium permanganate, and it's the elephant toothpaste reaction. It's a lot more exciting than this. Fairly safe, but not as safe. You could probably get a Tractor Supply. It's used as fertilizer. You should look it up. Yeah, look it up. Mark Rober has a video where he did the largest elephant toothpaste, and it was like a 20-meter tall Erlenmeyer flask thing. So similar, also a gas evolution reaction. Another reaction that we use almost every day is combustion reaction. So in an automobile engine, it's taking hydrocarbons. There's actually a lot of different types of hydrocarbons. Octane is one of them. And then it combines them with oxygen from the air, reacts to form carbon dioxide and water. And also generates a lot of heat and a lot of energy, and then we channel some of that energy into propelling the car forward, or propelling your car forward. And then this one is an oxidation reduction reaction. So it is generating gases, carbon dioxide, and water vapor, but it's more specifically an oxidation reduction reaction. And so when we get to the chapter 16 portion that I'm adding into chapter 7, we'll talk more about those. One that you might not have known was at work in your everyday life, laundry detergent. So laundry detergent actually has carbonate in it because there's, especially around here, have very hard water, unless you're fancy enough to have it a reverse osmosis. Probably not using that to wash your clothes, though. And so those calcium and magnesium ions interfere with the action of soap. So they'll get in the way of soap, they'll cause side reactions, they create soap scum, and your clothes won't come out as clean. But sodium bicarbonate, or sodium carbonate, not bicarbonate, will react with calcium and magnesium and form solid calcium carbonate, which is also limestone, and magnesium carbonate. And so once those solids are sort of dropped out of the solution, removed from the liquid, the soap can actually work better at cleaning your clothes. And then this is an example of a precipitation reaction, which is in a way similar to precipitation like rain. So the only difference is that rain is a liquid being formed in a gas. Most of the precipitation, actually all the precipitation reactions we'll talk about are a solid being formed in a liquid. So they are analogous. A lot of chemical reactions have or will have evidence that something is happening other than two things mixing. Because you can put salt into water, and while it's a little bit debatable, that is not a chemical reaction, right? It's just mixing. But when we have an actual chemical reaction, it's the atoms and molecules that compose matter coming apart and rearranging to form new atoms and molecules. And so all of the compounds that we've talked about up until this point can undergo different reactions. to become new things. We'll talk about some of the types of this, and you'll see a bunch of types of these reactions in lab today. A lot of cool colors. So because we can't see this happening at a molecular level, we've got to look for other signs, other evidence that reactions are happening. One of those is a color change. So like the molecules embedded in a child's temperature-sensitive spoon. Right? So the water's too hot, then it changes colors. It's actually causing a chemical change in the shape of the molecules that make the spoon red. So they no longer have a color. This is a special reversible one. So when you remove it, they revert back to the colored form. I have that same exact thing. Yeah. Or formation of a solid. So if you do get a precipitation reaction, you pour one liquid. So notice that this is a clear yellow liquid. So if something's completely dissolved, it'll be a clear solution. If there's anything floating around in it, then it's either a suspension, kind of like sand or dirt, floating in the water, or it's not actually dissolved. And then this is a clear solution here, but where the two meet, it's forming this cloudy solution. So this cloud is actually solid being formed from a reaction between the two liquids. You'll get to do that one today too. Another sign of a reaction is formation of a gas. Now sometimes you mix things together and it looks like they're forming gas, but really it's just air bubbles because you've shaken it or something. When you have gas forming, it's usually a very, very noticeable amount of gas and it doesn't go away after just a little bit. So Alka-Seltzer dissolving in water is a gas evolution reaction. Ones that are probably more familiar are things like heat absorption, emission, or light emission, especially heat emission, right? Anything burning is a chemical reaction. It's breaking apart those bonds and taking the energy that was bonding the atoms together, turning it into heat energy. Regular cold pack would not be a chemical reaction, but an instant cold pack, so it has something inside of it, kind of like it's like the opposite of like the hot hands, where that's actually iron oxide reacting with more oxygen to generate heat. There's instant cold packs where you break a thing inside, the chemical reaction absorbs heat. So that's a sign of a chemical reaction. And then glow sticks are also a chemical reaction. This is one example of not a chemical reaction, right? Bubbles being formed in water, if it's boiling, is not a chemical reaction. Because we're not taking the atom molecules, breaking the hydrogen and oxygen apart and forming new molecules. We're just changing states. So it's going from a liquid to a gas. Phase changes are not chemical reactions. Oh, and sometimes, yeah, chemical reactions can occur without any obvious sign. So you might not even be able to tell sometimes. So which of these changes involves a chemical reaction? A butane burning in a butane lighter. Why? How would you know that that's a chemical reaction? Light and heat, right? Yeah, so chemical produces what about butane evaporating out of a butane lighter? It's just changing states. So butane is a liquid in the lighter, and when you open it up without striking the flint, it's just going from a liquid to a gas. So we just say not chemical. Or phase or state change. Wood burning, chemical. Same reason as butane burning, right? Heat and light. Dry ice subliming. Huh? Oh, subliming means going straight from a solid to a gas. It's just a state change. Yeah, so it'd be a physical change. Physical, not chemical. It's a state change. That's why if you've ever bought dry ice, which it's like kind of expensive, but not really. It's a lot of fun to play with, great for Halloween, put it in punch, and it bubbles and makes mist and stuff. You can't really keep it for more than a day, because even if you put it in the freezer, it still sublimes in the freezer and will just eventually all turn to gas. Cool. So, oh, did I make the wrong molecule? I made the wrong molecule. Huh? Okay, so chemical equations, which you'll see more of these today, and I made the wrong molecule here. The chemical equations are how we write down what exactly is happening in a chemical reaction. So for example, if we have methane there, I need more bonds. So the CH4 is methane, so it's natural gas. It's reacting with oxygen, and it forms CO2 and water. So the left side of the arrow, it's read just like English, just like a sentence, left to right. The left side is what you're starting with. Those are your reactants. And then the right side is what's being produced. Those are the products. And then, and this question was asked about earlier, we've seen a lot of stuff where it's aqueous, so it'll be AQ in parentheses. But G represents gases. We'll have that on the next slide. But you can also think of chemical reactions kind of like Lego instructions. So in this case, we have methane, so black is carbon, and then the white ones are hydrogen, and then this is oxygen. So two red ones, oxygen. These ones are actually connected with a double bond. And what the chemical reaction is saying is, if I take one of these and one of these, I can rearrange all of these molecules to form those products. And so that's going to involve me taking, oh, actually, this one's not even balanced. All right, well, I'm not going to really bother balancing it now. So this reaction's not actually balanced, because you'll notice there's more oxygen on the right side than there is on the left side of the reaction. So chemical reactions need to be balanced, and we'll talk about this more. I need two of these and two of these. Unfortunately, I don't have enough pieces, I don't think, to make all those. But I can take these, and I'm rearranging these molecules, and I should have two of these, to make one CO2 and then two H2O molecules. So I'll pop all these hydrogens off, and then I can take these oxygens. I need one more here. Gonna take a second. Yeah, and as I said already, I need more waters. I would have needed to start with two oxygens. But then right now I've got CO2, carbon with two oxygens, and then water, and then I've got these two hydrogens left over, so I'd need another oxygen, but could make more. And those are always sort of breaking apart like that and recombining. So whenever you're seeing these things, try to imagine, and you can buy these kits, they're not super expensive. That's what's happening though, right? We're taking these things, breaking them apart, putting them back together, and we have to use all the pieces. There won't be any leftovers if you have enough of everything. So as for the states, these are the different state abbreviations. So you have gas, liquid, solid. Those are pretty self-explanatory. The aqueous just means that it's a water solution, so it's something dissolved in or mixed with water. Oh, yeah, see, so, yeah, our left side had two oxygen atoms. And then our right side here had 3 oxygen atoms, but matter has to be conserved. Right? We cannot generate new atoms, or you can't generate new Lego pieces out of nowhere. They have to be there in the sort of initial set, in the pieces that go in. Yeah, so because of this, we have to balance it, and so we're going to need different numbers to make the products and the reactants equal. So to correct for this, so the left side also has 4 hydrogens, and the right side only has 2 hydrogens. So we need to fix that too. And that's where we'll get to balancing chemical equations. So when we're balancing a chemical equation, we insert coefficients and not subscripts in front of the formulas to make numbers of each type of atom the same on both sides of the equation. If we change the subscripts, if we change these numbers, then we are actually changing that type of atom. And it becomes or that type of molecule. It becomes a different molecule. So the only thing we can do in a chemical reaction is get more oxygen, really, in this case molecules, or more methane, or more CO2, or more water. And so that's what the coefficient says. That number in front says we need 2 oxygen atoms, right? 1, 2, and we'll produce 2 water molecules. And I like to think of these like a puzzle, because it's really what they are. As long as the chemical reaction is written down correctly, it'll always work out. It's kind of just like a Sudoku. You got to figure out which numbers fit in, follow the rules, and solve the puzzle. And this is also where nomenclature is going to be more important. So to write out a balanced chemical equation, if you just have chemical names, then you need to be able to correctly write out the formulas from those names. Because if you write out the incorrect formulas, it's not going to balance properly. So we start by writing a skeletal equation. And that skeletal equation would be like the CH4 plus O2. We'll make CO2 plus H2O. If you'll notice, I'm leaving a little bit of space in front of everything so that there's room to put coefficients in later. So this is the skeletal, right? It's unfinished. We haven't balanced it, but we've got all the chemicals in with the correct names, or with the correct formulas. And then, again, these are puzzles, so there's multiple ways to solve a puzzle. Some tips, though: if an element occurs in only one compound on both sides, balance it first. So in this case, we can look here and we say, oh, whoops, CH4 has carbon, and CO2 has carbon, so it's existing in one compound on either side. Unlike oxygen, so oxygen's only part of this oxygen molecule here, O2, but it's in CO2 and it's in water. So if I put a coefficient here, that changes the number of oxygens, and then I have 2 different places where I can change the number of oxygens on the product side. So it'll make things more complicated. So you want to start with something like carbon or even hydrogen, which exists in one compound on both sides of the reaction. And then if there's more than one such element, and this example doesn't have any metals in it, then you balance the metals first. I feel like this is kind of like explaining rules for like a board game, where I can explain all the rules to you, but it takes more context to actually put those rules into play and to understand where those rules make sense. So we'll get there. Let me do this. Copy that down here. So if an element occurs as a free element on either side of the equation, balance it last. So example in this reaction is oxygen. Oxygen there exists as a free element. It is O2, but it's oxygen. It exists as a diatomic, right? It's Brinkelhoff, one of the diatomic elements. And then you always balance free elements by adjusting the coefficient on the free element. So we would add a coefficient here if we needed to. We wouldn't start here and then balance a coefficient on the other side to balance oxygen. And then if the balance equation contains coefficient fractions, can happen sometimes, then you change those into whole numbers by multiplying the entire equation by the appropriate factor. So actually in this case, we have O2, and we have 2 oxygens, 1 oxygen there, so there's 3 total oxygens on the product side. So just talking about oxygen here, if I wanted to balance this, I could write 3 over 2. So 3 over 2 times 2 oxygens in O2 would give us 3 total oxygen atoms. But we can't have half of that oxygen molecule. So we would multiply the entire thing by 2. So it would be 2 CH4 plus 3 O2, 2 CO2 plus 2 H2O. So multiplying everything by 2 gets rid of that fraction and makes it a whole number 3. Okay. And then finally at the end, you check to make certain the equation is balanced by summing the total number of each type of atom on both sides. So do change the coefficients, do not change subscripts. As we'll sort of get to this later, sometimes you'll have to predict what the products of a reaction are. And then the only time you change subscripts is to balance charges when you're creating new ionic compounds. And that's an initial step. But then you're changing, yeah. We'll get there. All right, so I want to write a balanced equation for the reaction between solid chromium oxide and solid carbon to produce solid chromium and carbon dioxide gas. So this is why we did nomenclature. Okay, so I'm gonna highlight here our compounds that we're looking at. We have chromium, actually solid chromium, solid carbon, we're going to produce solid chromium and carbon dioxide gas. So this sentence here is actually telling us where to put all of these compounds, right? Chromium oxide and carbon are going to be reactants because those two, well, it says reaction between chromium oxide, solid carbon. Those are reactants to produce solid chromium and carbon dioxide gas. Those will be the products. So what would chromium oxide, what would that formula be? Yeah. So it could start with Cr3 plus and then O2 minus. So the 3 plus here, that's chromium 3. So this is going to be Cr2O3 plus solid carbon. It's just going to be C. Yeah, so the C2, or the Brinkelhoff compounds are, I say Brinkelhoff because that's the mnemonic that I use. There's bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Those all exist as diatomic gases. Okay, so we can even write here, this is going to be solid, this is solid, and we're producing solid chromium. So it's just going to be Cr. That's a solid. Did a bad job of leaving spaces for prefixes, or for coefficients. And then carbon dioxide gas. So carbon dioxide is a molecular compound. We know that because it says dioxide. So it's going to be CO2, and that's a gas. All right, so that's our skeletal chemical reaction. Actually, to keep that, I'm going to do this. So now we need to balance all of the elements on both sides. So to go back and follow our rules, rule number 1 here is, well, writing a skeletal equation. So we wrote a skeletal equation with the correct formulas. And then if an element occurs in only one compound on both sides of the equation, balance it first. If there's more than one such element, balance metals before nonmetals. Okay, so come back to this. So we want to balance elements that exist in only one compound on either side. So which elements exist only in one compound on either side? There's 2. Chromium is one of them. And then carbon is another one. And actually, oxygen also only exists on both sides. But since we do have a metal here, we're going to balance chromium first. And that conveniently leads into one of the other rules. So go back to that. If an element occurs as a free element on either side of the chemical equation, balance it last. They all kind of exist as free elements. Always balance free elements by adjusting the coefficients on the free element. Oh, actually. So chromium exists as a free element, so we're going to balance that. Not going to balance that yet. We want to balance oxygen, actually, because it doesn't exist as a free element. It's the only thing that doesn't exist as a free element. So how do we balance oxygen? Yeah, so we can kind of use the crisscross rule here, and we want to get the least common multiple, the smallest common multiple. So this is 3, this is 2 oxygens. So if we multiply the 3 by 2, so add a 2 subscript here, or coefficient here, not a subscript. And then we add a 3 coefficient over here. Now we'll have 6 oxygens on either side. Alrighty. Now we're to our 2 of our elements that exist only on one side. So we want to balance chromium first. So how many chromiums are in our reactants? 4? So there's 4 here because there's 2 chromium 2 oxides, or chromium 3 oxides, and there's 2 chromiums in each of those. So 2 times 2 is 4. So we can take a coefficient of 4 on the right side on our products. And then for carbon, right, last thing remaining that's not balanced. This is 3 carbons, so we can just put a 3 on the other side. So as our final check here, we can count up the number of each type of element. So we've got chromium, oxygen, and carbon. So we have, and then there's chromium, oxygen, and carbon. My recommendation for what order you do these in, the order doesn't really matter. Usually I just go to the reactant side and I'll go just left to right and order them that way. And then I do the same order on the product side, because that way I can just look at them one to one and make sure that they're matched. So this is going to be 4 chromium. How many oxygens? 6. 3 carbons. And then this will be 4 chromiums because it's got a coefficient of 4. Then 6 oxygens and 3 carbons. So same number on either side. The only time that you don't write things out as elements is if you have polyatomic ions. And the polyatomic ion stays the same on the left and the right. It's going to make your life a whole lot easier to balance polyatomic ions as individual things. Trying to think where else we've done it. Oh, the same way that you would treat them for nomenclature. All right, any questions? Balancing. We'll do just so much more balancing, so move this to the other side. All right, so write a balanced equation for the combustion reaction of gaseous C4H10, so butane, and gaseous oxygen to form gaseous carbon dioxide and gaseous water. So C4H10, oxygen, carbon dioxide, water. And gaseous just means it's a gas. So what are our products or reactants going to be? C4, H10, and then G goes in parentheses, plus O2. And then our products.
CO2G and H2OG.
Mm-hmm. So in a question like this is where you do need to know that gaseous oxygen is always O2. Again, that's because bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, if any of those is written as either elemental or gaseous or anything to indicate that it's the element by itself, not part of a compound, it'll be like Br2 or I2, or in this case, O2. That is their elemental form. Okay, so what should we balance first? There's 2 valid options. Carbon works. What would the other option be? Hydrogen. Why carbon and hydrogen?
Because they're 1-to-1 ratio on each side from the reactant to the...
Yeah, they're only part of one compound on either side. So our oxygen here is in carbon dioxide and H2O, carbon dioxide and water. And it's also a free element on one side, so we want to balance that last, because if we change the coefficient for O2, it's not going to affect anything else. So we'll balance carbon first. So how many carbons are there in the reactants? Yes, there are 4, coefficient 4. And then again, we don't want to balance oxygen yet because we can come back for oxygen and balance it pretty easily with this O2. So for hydrogen, and somebody knew this time, how many hydrogens are there in the reactants? Oh, in the reactants. Yeah, there's 2 in the products. 10. Yes, there's 10 here, and then there's 2 over here. Yep, at a coefficient of 5. And now we can balance the oxygens, because carbon and hydrogen are both balanced. So this is going to be 4 times 2. So there's going to be 8 oxygens there. just going to do a tally on the right here. 8 oxygens there, and then there's also oxygen and water, and that's 5 times the 1 oxygen per water. So it's going to be another 5. So we're going to have 13 total oxygens now in our products. And then this is the trick, and this is why you want to use fractions sometimes. Because obviously we can't take 13 and divide it evenly into the 2 to get a whole number. But we can just write 13 over 2, which does give us a fraction. But what number do we now multiply all of the coefficients by? 2. And just make sure you actually go through and multiply all of them by 2. So this will be 2 C4H10 gas plus 13 O2 gas is 8 CO2 gas, 10 H2O gas. And now we can do our final check. Feel like a flight attendant, or the, I guess, pilot maybe, doing our final flight check. So we have carbon, hydrogen, and oxygen in our reactants. Again, just going left to right here, carbon, hydrogen, oxygen. And then this is where I mean, like, I just copy the order from the reactant side, because now on the right side would be carbon, oxygen, and then hydrogen. But it's easier to compare if we do them in the same order. So in our reactants, on the left side, how many carbon atoms do we have? 8. How many hydrogen atoms? Yep, 20. How many oxygen atoms? 26. And then in our products, 8 carbons again. And then hydrogens, it's going to be over here, right? 10 times 2. So it's 20. And then the oxygens, you just have to remember oxygen is in 2 places now, so you have to do both. And so this should be 8 times 2. So I can write it like this. We do 16 plus 10 oxygens from water. So total of 26 oxygens. So it is balanced. They'd need a lot of model kits to show that. All right. There's some of them, so if you ever get, so this is a combustion reaction, right? This is butane, C4 is butane, and we're burning it, reacting with oxygen, forms CO2 and water. That is like the hallmark sign of a combustion reaction, by the way. If you have, the products are just CO2 and water, or if you have something that is carbon and hydrogen being reacted with oxygen, and it's going to produce CO2 and water. These are the ones that most often end up having a fraction in front of oxygen, and then you have to multiply everything by 2. Some chemical reactions are easier to balance than others. So we write a balanced equation for the reaction of aqueous lead acetate with aqueous potassium iodide to form solid lead iodide and aqueous potassium acetate. So aqueous lead acetate. What? Okay, smart highlighter, thanks. Aqueous potassium iodide to form solid lead iodide and aqueous potassium acetate. Wouldn't necessarily expect you, no, I guess you should know. No, I didn't make you learn the names of these. So acetate's one of the ions, polyatomic ions. C2H3. Oh, and this is the one that's wrong on the worksheet. So C2H3O2, 1 minus. So what would lead acetate be? This is going to be a Pb2 plus and a C2H3O2 minus. And this is what I was saying, adding, right, got to change the coefficients to make the charges balance. So this compound, lead acetate, would be PbC2H3O2 2. And what would potassium iodide be? What's the symbol for potassium?
K.
And it has a charge of
Plus.
plus. And iodide,
I minus.
be I minus. So potassium iodide is, we gotta, yeah, so how many potassium, how many iodine?
1 and
1 and 1. Yeah, so Ki. All right, and then our products are going to be solid lead iodide. So what would that chemical formula be? Just spell it out with letters.
PBI.
PBI, would it just be 1 iodine?
2.
2 iodines. I will definitely have a problem like this. Maybe not with acetate. I probably won't throw acetate in. There would be problems where you have to know the nomenclature to be able to write down the chemical formula to be able to balance the reaction. So make sure you go back and review nomenclature. Use that extra study guide, nomenclature study guide that I put on Canvas. And then potassium acetate. It's going to be K, and then our acetate, C2H3O2. We only need one of those because potassium has a 1 plus charge, acetate has a 1 minus charge. And then this is also where I was talking about treat polyatomic ions as if they are a single element by itself. Right? So don't try to balance in this problem the number of carbons, hydrogens, and oxygens separately. Makes it a lot easier if you treat acetate as 1 unit because it acts like 1 unit. So if we balance acetate on one side, acetate will be balanced on the other side. Now, is there anything in particular we should start with on this problem? I would say no. Right? There's nothing that exists as a single element. Everything is only part of one compound on either side. So usually in this scenario, I'll just start on the left. So if we start with lead, and my strategy for problems like this, where there's no obvious starting point, is start with something, and then just sort of bounce from one element to the other, balancing things as you need to. So if we start with lead, say, okay, we have 1 lead on this side, and we go over to the other side, we say, oh, there's only 1 lead here. Cool. Then I'll balance the next element there, iodine, or iodide. So there's 2 iodides there. And then we'll look over to this side and say, oh, iodine is here, but there's only 1 of them. So I'll add a coefficient of 2. So now iodide is balanced, but that changes potassium. So I say, okay, well now I've got 2 potassiums, and so I'll go back over to the product side, see how many potassiums I have there. Oh, there's only 1 potassium. So then I'll add a 2. So now we've got 2 potassiums. And then look at what potassium is bound to, and it's acetate. And so I'll go over here. I'll say acetate, we have 2 acetates, and then on the reactant side, we have 2 acetates. And then you go back to lead, but lead is already balanced. So if there's no obvious starting place, start on the left, and then choose one of those two elements, follow that to wherever it's on the product side, balance it. Whatever it's bound to will change if you change something, and then we keep bouncing back and forth between the products and reactants until everything's balanced. So now we can count these. We have lead, and again, treat acetate sort of like it is an element. So we have lead, we have acetate, and we have potassium, and we have iodine. Lead, acetate, potassium, and iodide. So how many lead do we have in the reactants? Just one. How many acetates? Two. Potassium? Iodide? Two. And then on our products, we have one lead. How many acetate? Two. How many potassiums? And iodide? Yeah. So it's balanced. Any questions? Cool. So I won't make all of the problems like that where you have to solve or figure out what each of the element formulas is from the names, then write it out as a chemical reaction, and then balance it. That'll be like a last problem kind of question. Some of them would be like this. So where should we start on this one? Somebody say hydrogen? Now, I will say, while I gave you those rules, right? But this is a puzzle. It's like Sudoku. You don't have to follow. There are no set rules except for every row has to have 1 through 9, and every box has to have 1 through 9. And there can't be any duplicates. So there's more than one way to solve a balanced chemical reaction. There are some things that might make it easier. I would start with hydrogen here, because we have oxygen by itself and chlorine by itself in their elemental forms. But that isn't to say that you couldn't start with one of those. So we balance hydrogen first. Hydrogen, hydrogen. So we have 2 in the products, 1 in the reactants. So we'll add a 2 here. And then that changes the number of chlorines. So then I'll say, okay, now I have 2 chlorines, and there's already 2 over there. So now we have to balance oxygens. So if we take this oxygen, and this is where that one of those rules comes into play. If I balance this oxygen with this over here, there's 2 here, there's 1 here. If I put, I'll do this in a different color. If I put a 2, that changes the number of hydrogens. And now I'm going to go back over here. I'm going to change the number of, now I'm going to change the number of hydrogens here. And then that's going to change the number of chlorines. And I guess eventually you'll get there. But if instead we balance the oxygen on the side where it's the single oxygen by itself, and we say, like we did with the 13/2, now we want one of these 2 oxygens. We'll say, so switch back to black. We'll say half of that. Now we just take everything and multiply by 2. And so we'll get 4 HCl plus 1 oxygen, 2 H2O plus 2 Cl2. If it comes down to a situation like this, where yeah, it's
Yeah, like how am I going to know when I need to use a fraction?
yeah. So it'll be if you have an odd number of oxygens. It's usually oxygen that does this. So if there's an odd number of oxygens on one side and an even number on the other side, then you're going to have to use a fraction for O2. In this case, this is the other scenario where you want to change the coefficient in front of the elemental oxygen by itself so that it's not changing other things. That's when you would use a fraction like this to do 1/2. Instead of putting a 2 here and then having that change the number of hydrogens and then having to erase this, change that to 4, and go through the whole thing.
So we would multiply it by 2 because 2 halves equals a whole.
Yeah.
Okay.
Yeah. Alrighty. So it's the start of chemical